bon dia, buenos dias. I am happy. I'm happy to welcome you to the fourth day of the conference. Remember that we have a dinner tonight to celebrate Carsten's birthday. We are very happy here celebrating Carsten's birthday. And it's my pleasure to introduce Laura De Marco from Harvard University, who will talk about Lattès maps and bifurcations.
Microphone working? Oh, now I hear it. All right, thank you. All right, again, special thanks to Luna. There she is. And of course, it's an honor to be here to celebrate Carsten's birthday and his research and his legacy, what he's done, and the impact that it's had on all of us. And as many of you know, a lot of the research that I've been doing for the past 10 years, say, is not so closely related to the work of Carsten, but I chose a topic that actually has brought me back to thinking a lot about bifurcations in holomorphic families of rational maps, actually related to Lattès maps specifically. So this image here, this picture, is a very rough approximation to a bifurcation locus, which happens to be the entire complex plane in this example. And so this was just a picture. I was trying to get a sense of a certain distribution on this plane. But anyways, I'll come to this at the end, hopefully. But in my talk, I want to start at the beginning, not at the end, and really at the beginning. So by the beginning, I mean the beginning of our field. So you don't have to read the text on the screen. This is just the English translation of the original announcement of the prize, that the competition that started it all, that was announced in 1915, and which prompted the research of Fatou and Julia, the ones that we refer to all the time. The goal of the problem, as many of you are probably aware, was to, well, it says here, up to the present, the most well-known works related to what's now the field of dynamical systems have been devoted exclusively to the local point of view. And the goal of this prize was to encourage people to start thinking more globally about dynamical systems, but specifically in the case of iterating, say, rational functions. It says where this map, F, might depend rationally, for example, on the point. And as we know, of course, this has now led to a wonderful history and a very, very rich and exciting subject of studying complex dynamics and all its different flavors. But especially I want to mention, so at the time, the work of Fatou and Julia and Montel, most celebrated works. By the way, this prize, there were actually only, the prize closed in 1918. So researchers had a few years to think about this. There were only 3 submissions. Many of you may know this history already. There were only 3 submissions, but not these 3. Of these 3, only Gaston Julia submitted a manuscript for consideration. Fatou had done his work at the same time, as I think all of you might know, but did not submit his work, perhaps because he knew that Julia was planning to submit. I don't know the reason he did not. Both of them were building on the work that had already appeared of Montel, as we know, on the theory of normal families of holomorphic functions.
Laura, do you know who decided that this should be an important thing?
I don't remember.
Decision,
Yeah, I don't remember who was behind this particular decision, but there's. Did I have on the previous slide the reference here? Yeah, so in this book, this is a version of the book published 10 years ago, is what I was looking at. There are earlier versions, too, that some of you may have seen. In any case, there's a lot of the history in there, and I'm pretty sure it says who the jury was and who posted it and everything else. Yeah, Andre, what?
So moving from real to complex is in this last paragraph? The entire domain of value?
No, I don't think that the solicitation necessarily insisted upon complex. I don't think so. So it could very well have been real. And one of the submissions, the third one that no one cares about, I think, was actually focused on real dynamics. But I don't know. I don't remember, and I'm not a historian. But the part that I want to focus on was there was Julia, and then a third one, and now I've forgotten who it was. But and then there was the submission of Samuel Lattès. And many of us here in this room are familiar with the work of Lattès, only in the sense that we have a class of maps named after him. So Lattès was the runner-up. He won a sort of second prize. Sadly, Lattès died that year in 1918 of typhus, and he was not alive to receive his prize, but his family received the money that he was owed. And so I want to talk about what Lattès did and then how it relates to what I'm doing now and how it relates to bifurcations and holomorphic dynamics and beyond. And so let me say a little bit about the work of Lattès. He was studying functional equations of the following sort, where so composition relations between holomorphic or meromorphic functions. The P here is specifically the Weierstrass P function. And L is a linear map from C to C, so lambda is some complex number. And then it was trying to understand which rational functions F fit into a commutative diagram of this sort. And by the way, I guess studying functional equations of this sort was a natural thing to do, especially at the time, and there was quite a bit of work on these functional relationships related to composition. In fact, soon after the work of Lattès, I want to mention in the work of Joseph Ritt, whose work I believe was mentioned maybe was it Davoud's talk? The work of Ritt, where he actually completely answered the question, in the case where all four maps are polynomials, the questions of how you can decompose polynomials in possibly two different ways as compositions of other polynomials, he gave a complete classification in the 1920s, so shortly after this work and other work on functional equations. So the polynomial case is completely understood. By the way, the case of rational functions, to really completely understand how two rational functions, or how a rational function might be decomposed in two different ways into rational compositions is not yet fully understood. We certainly know a lot more than we did back in the 1920s, but there's still some open questions there. In any case, what Lattès was working on was this setting. So we have the Weierstrass P function here, this doubly periodic meromorphic function, and linear on the top, and then F on the bottom. OK, so now I guess most of us know what these maps are. These are exactly the maps F that we call the Lattès maps, the ones that arise in this fashion. So of course, this Weierstrass P function, being doubly periodic, factors through a torus, the quotient of the complex plane by those periods, forming a lattice here, lambda. So I'm viewing this as an elliptic curve. Notice I've put a little dot here to indicate my elliptic curve is not just a torus, it's actually a group. I have a 0, and that little dot represents the 0. In any case, so this P function factors through the torus, through this elliptic curve, via then this quotient, where you glue a point to its additive inverse. We have a group structure, and the Lattès map is the one that's induced down here. And there's a wonderful reference on actually some of the history of this work and how to describe these Lattès maps and a classification of these Lattès maps given in this article of Milner that appeared already some years ago. And so I encourage you to read that if you haven't already. What I wanted to say is that this is not just an abstract construction. The Fs that you get, you can write down. We can write down formulas for these maps F. So for example, if you take the linear transformation multiplication by 2, which will preserve any given lattice in the plane. Let's take the square lattice, for example, generated by 1 and I. That gives you what we call the square torus as its quotient. And that particular map, if you choose coordinates on your Riemann sphere, gives you, for example, this formula in some choice of coordinates. So you can write these things down very explicitly and work with them and compute with them. From a point of view of the original competition, I guess one of the reasons Lattès was not granted the main prize, I think the researchers at the time didn't find this very interesting. I mean, this produced an example, example of a dynamical system on the Riemann sphere, which, as we will see, has a dense set of periodic points. And I think that was his main goal, was to exhibit these interesting examples with a dense set of periodic points in the entire Riemann sphere. But Fatou and Julia weren't really so, and the others were not so interested in that result at the time. By the way, so I thought this was amusing. So if you look at the original article in 1918, this one, which I had chosen for this talk, but hadn't, without having gone back to look at his article, happens to be exactly an example that Lattès provides in his article. You'll see you have the Weierstrass P function. U is his variable on the complex plane, multiplication by 2. It's the square lattice. But amusingly here, there's a typo in the paper. Of course, if you had z squared minus 1 in the numerator and in the denominator, they would cancel. So this is certainly not the correct formula. So I never noticed this before until just a few weeks ago looking at this. In any case, that's supposed to be a plus sign in the numerator. Yeah, anyhow, so that's the original article of Lattès, and this was an example that he was looking at. All right. OK, so Lattès maps. OK, maybe not so interesting from a dynamical point of view in the sense that we believe we understand them as dynamical systems completely. They're linear on C, linear on the corresponding torus, and the quotient of linear on the Riemann sphere. So here's a basic observation that I'd like you to keep in mind, which is related to the theme of the talk and the results that I want to present, is the following. So just to remind you again, so the elliptic curve is a group. Okay, so it has an additive group structure. And suppose I choose as my linear map just multiplication by 2. So in other words, adding a point to itself on the elliptic curve. And I'm going to choose this one. There's nothing special about 2. I just want to choose one that exists for any elliptic curve, not just for the square lattice, not just for any particular lattice, but one that could exist in a family. We know that those give rise to the flexible Lattès maps. Remember just vocabulary. Remember that a point is said to be torsion if it has finite order for the group. And we know that a point is preperiodic if it has a finite orbit for a dynamical system. And a very elementary observation from the definitions is that a point up here is torsion for the group structure if and only if it has a finite orbit under multiplication by 2, which in turn corresponds to having a finite orbit for the Lattès maps. Okay. So this is just very basic, just writing down what it means to be torsion, what it means to be preperiodic. And so here, this picture is supposed to indicate, as I said, so that the torsion points are dense in the elliptic curve itself. They just come from the rational multiples of the lattice points in the complex plane, and then picturing them here in the torus. So this polka dot picture is supposed to be my dense set of torsion points. And then these project, as I said now, to a dense set of preperiodic points in the quotient. So as I said a moment ago, in particular, the preperiodic points are dense in the Riemann sphere. Okay. So I said this is an elementary observation, but again, I want you to hold on to this relationship between torsion points and preperiodic points, because this connection is what actually has led to a number of the projects that I've been working on, which were actually questions about that originated in arithmetic questions related to elliptic curves that we could get a handle on by thinking of them dynamically. Okay. So I want to show you an example of such a question, which has led to relations to bifurcations, although it's not going to be obvious from the statement. All right, so here's an example question. I learned about it first from a paper of Bogomolov and Chinkel that appeared in 2007. The same question was revisited about 10 years later in a collaboration with Hong Fu. And the question is the following. Suppose you're given two elliptic curves, E1 and E2, and you project each of them down to the Riemann sphere via the same type of projection, just as I had before, where you glue a point to its additive inverse, and the quotient will be the Riemann sphere. I'm working over the field of complex numbers right now. And the question is, how large is the overlap of the projection of the torsion subgroup? Remember this. Here I have the picture. How large is the overlap of the projection of the torsion points from each of these elliptic curves? So on the left side, I have a dense set of torsion points here. Remember, I have a dense set of torsion points on this other elliptic curve, and then I'm projecting them to, say, two dense sets on the Riemann sphere, and the question is simply, how big can that intersection be? How big can that intersection be? So formulated in this way, it's kind of a quirky question. Doesn't sound very well motivated. I should just mention that this is one question in a family of many questions that have been addressed over the last 40 or 50 years, in some sense related to how the geometry of an elliptic curve or an abelian variety more generally, and the structure, the geometry of its subset of torsion points can be related to, say, the arithmetic of the object. For example, knowing some collection of torsion points, do we know what field this E is defined over? Or looking in a larger space, in an abelian variety, looking at subsets of torsion points. You look at their closure in the Zariski topology, and you want to understand what kind of objects can you get. So there's a long history of questions of this flavor that I won't go into, but I hope you can understand at least this one question. How large is the overlap of these two infinite sets? Well, I guess the first observation is that either those two projections are equal as sets, or the intersection is finite. Okay. It turns out this is not completely trivial to show, and the only proofs, even though I'm working over complex, the only proofs that I'm aware of go through arithmetic methods. And so I just want to mention that the intersection will be finite of these two dense sets. The intersection is finite unless they're actually the same or isomorphic elliptic curves, and the projections are the same, with the same sets of coordinates on the Riemann sphere. Okay, so basically that the elliptic curve and the corresponding projection, they're the same pair. That's the only way you get an infinite intersection, because as soon as it's infinite, it turns out, click, they line up into place. They're really exactly the same. And in the article of Bogomolov and Chinkel associated to this very particular problem, they observed this as a corollary of a famous theorem of Raynaud, proving the Munning-Mumford conjecture in the early 80s. Another proof can be given, building on the theory of arithmetic equidistribution. And in fact, in some of my own work, we wrote out another proof of a result of this sort, developing upon arithmetic equidistribution, which is actually many people's results, but really going back to some ideas from the late 90s of some number theorists. OK, so this is a finite intersection. OK, so then how big can it be? So it's at least a finite intersection, so it makes sense to talk about its size. How big? How big? Well, we don't know the answer. We don't know the answer. Maybe I'll just remark that the largest known intersection is an example of a very recent example of Fu and Stoll, where that intersection of the torsion sets has size 34. That's the largest known intersection for any pair of elliptic curves. It probably is the largest intersection. I would believe that it can't actually get any bigger. But we don't know how big it can get. But the one thing we do know for sure, is that that intersection, the size of the intersection is uniformly bounded over all pairs, over all pairs of elliptic curves, I mean, together with their projections. Maybe it's worth mentioning that there's like a, I keep breaking the chalk. There's a moduli space of such pairs that you could work with, and it's probably worth mentioning that, I guess they're pairs of pairs, really. A moduli space of pairs of pairs. In any case, the dimension of this space over C is actually 5. I hope the notation makes sense. I don't want to be precise here. When the moduli space of elliptic curves is one-dimensional, as we know. So if you have a pair of them, that's two-dimensional. But then we have Mobius transformations changing your projection. So that's another 3 dimensions. So you can change on just for one of them, but not the other, if you want to pin down a class. In any case, there's a 5-dimensional space of such things. The work that I'm mentioning of my own here only handles a 2-dimensional subspace, so we didn't prove the whole thing. But now, in a brand new preprint of Jerome Poineau from this year, he was able to push these methods to get us all the way to the full space, to get a uniform bound. And in fact, it also follows, though not explicitly stated, from some very recent work of Gauge and Kuhne. And anyways, what I want to emphasize, so this uniform bound here, well, it's very specific to this setting, this proof. However, it fits, just as the question, I said, fits into a family of questions about torsion structure and geometry of abelian varieties and arithmetic of abelian varieties. This here also fits into a family of questions about uniform bounds in the setting of families of abelian varieties, especially, and in the most famous example would be the results from this year or last year on uniform versions of the Mordell conjecture. Given an algebraic curve over some number field, can you uniformly bound the number of rational points on that curve? Almost, as long as so in terms of the genus of the curve and in terms of its Mordell-Weil rank. So in any case, there are brand new breakthrough results in this area. And so I just wanted to mention, to sort of compare this statement to some of the recent results, if you're familiar with them, in arithmetic geometry. OK, so why am I talking about this result here? This is not really about bifurcations, but it is about complex dynamics, because, as I mentioned earlier, of course, these below each of these elliptic curves, I have a Lattès map. So really what I'm looking at is 2 different Lattès maps and their sets of pre-periodic points. Yeah, question?
Do you know what M is?
I do not. So as I said, so the largest known is 34. The proof can be made effective, though it's not, but it leads to a bound of roughly 10 to the power 100, which is way bigger than 34. So that's just an artifact of the proof, that the way the methods give you something, but not something very useful. But I would guess that this is actually the optimal bound. And I think generally, if you work in a Zariski dense set, I think the optimal bound will be 5. So anyways, so I have some ideas, but I don't know, actually. So the proof that we give actually goes through the fact that these are Lattès maps. So in fact, we're really working with the dynamics. And so it was very natural to ask then, more generally, suppose now I have a pair of dynamical systems, in this case rational functions on P1, how big can this intersection be between their sets of pre-periodic points? So I wrote it here. Given 2 maps from P1 to P1, so just down here, just not Lattès maps, some other kind of map, how large is this intersection of the pre-periodic points? Okay. And maybe I should mention at this point, I wasn't going to get into the details here, but to make sense of this question, of course, I want to assume, to make sense of this question, it's helpful to assume, if you're going to deal with arbitrary rational maps, I want to assume that their pre-periodic points are not equal, as would be the case if they share an iterate, or are the same map, or are related in some way. Equality of pre-periodic points, it turns out, is essentially equivalent to having a relation. And so I'm not going to write down the details of that, but just to make sense of this question, we'd of course want to assume that they aren't already the same map. Otherwise, of course, this can be as large as you want. Also, it's helpful when thinking about this question to assume that the degrees are bounded. So maybe assume also that the degree of f and the degree of g is less than some constant to even talk about this. Because you can certainly build examples of rational maps that share as many, say, fixed points as you want if you allow your degree to grow to infinity. So you can certainly build examples in this way. And some of you have seen me talk about questions of this sort. For example, at Misha Lubitsch's birthday conference, I spoke about bounding this intersection of sets in the special case of quadratic polynomials. And Carsten, I think, saw me speak earlier this year about also a similar question where it was sort of a preliminary work in this direction to try to attack higher degree maps. The issue, though, is that these proofs and the ingredients and related results are really special to the setting. These are elliptic curves. I mean, we've got a lot of structure here that we don't have in general. I mean, here's a picture. So suppose you have two quadratic rational maps, quadratic polynomials, say z squared minus 1 and some other quadratic polynomial. I mean, we don't have group structure anymore. We could try to study the intersections of their pre-periodic points. So here's just a superposition of the two filled Julia sets. You can see that these fractals overlap in complicated ways, and it's not clear that if you were to move the sets around, maybe you could get larger and larger intersections. The proofs there were very special to the group setting. And the proof in the case of quadratic polynomials, for those of you who've seen me talk about this, was also very special to the setting of quadratic polynomials. OK, so I guess the main thing I want to mention is that indeed now we have almost a uniform bound for all pairs of a given degree. And I say almost because it's actually just a general result in the following sense. So this we've just written up. We haven't made it available yet. For every degree, if you fix the degree and you look at pairs f and g of just of that degree, then the statement is, as long as you cut out a certain subvariety, a certain algebraic subvariety, then you can get a uniform bound on the size of the intersection of the sets of pre-periodic points. So it's saying for general pairs, f and g, we actually have a uniform bound in every degree. Okay. But again, just one more time to emphasize, you cannot have a uniform bound for all maps of a given degree because there are always pairs where you have equality here. F equals g will always give rise to equality. So you have to exclude those. And we expect that those are the only things to exclude, is those obvious exclusions, but we have not yet proved that. Yeah?
Is V sub D codimension 1?
Yes. It could be higher codimension. No, we don't have an explicit description. I mean, I know it's contained in a codimension 1 thing. At this stage, I have not given an explicit description of it. But work in progress, we want to say V sub D is equal. So let's say next goal is to say V sub D is just equal to the set of pairs where the pre-periodic points, in fact, coincide, which will then have codimension much larger than 1, in fact. Yeah. It'll have half dimension, I guess. Yes, as a subvariety of the space of all, as a subvariety, yes. Yeah, it's not obvious that this has an algebraic description because of the way it's defined. But it turns out, as a consequence of work of Levin and Przyczynski from years ago, and some more recent work of actually some of the authors I mentioned, Yuan Zhang, myself, and Matt Baker, you can actually describe this algebraically. Yeah. But that's not totally obvious. I mean, it needs argument. But it is actually an algebraic subvariety. So the statement itself is maybe not so interesting, actually. What I find more interesting is the proof because the way to go from results about a billion varieties to now something about holomorphic dynamical systems without a group structure, there is an aspect of these proofs. So we actually use ingredients from their proofs. So it's really brand new results that we're taking and realizing, there is something here which has a dynamical interpretation, not just group theoretic, but actually dynamical, and that's what we use. So just to summarize in one sentence, and then I'll say more because I want to show you some pictures, is what we're really doing is taking ideas from the theory of stability and bifurcations and holomorphic dynamics combined with what they did, with what was done in these results about a billion varieties, anyways, building on a number of authors' very recent work. These are all names associated to preprints from last year and the year before, and this year too, maybe, sort of incorporating the arithmetic ideas combined with stability and holomorphic dynamics. And at the end of the day, what you get is a proof of this general result for arbitrary degree, but also a new proof for the Lattès case that I mentioned before, where you really know that the only exceptions in the Lattès case is this, and you can get that as well. And it's also true for quadratic polynomials, which was something I had proved before, but there again, you know all the exceptions. The only exceptions in the case of quadratic polynomials are the ones where they're the same map.
The all here is new, or the all was also?
No, sorry, that was also new. Yeah, so I mean, that was also there. So the theorem in this paper said for all pairs of quadratic polynomials that are not the same, that are of this form, but not the same one, there is a uniform bound that holds.
So it's the same statement.
Same statement, sorry. And by all, I'm saying it's stronger than what I wrote here. Because here, this is a general result. I'm excluding some mysterious subvariety of pairs. But I don't think you really need that. That's an artifact of our ignorance at the moment.
Sorry, to go back like 3 slides, maybe. You don't need to, but in the Lattès case, the bound doesn't even depend on the degree of the map.
Right, because so as a dynamical family, you can make them all degree 4. So I could just take the ×2 map that I used before, and so as a family of dynamical systems, I can just assume they're all degree 4. Doesn't matter which Lattès, so that the structure of the pre-periodic points in the case of Lattès maps only depends on the elliptic curve and not the map you choose, because of that relation between torsion and pre-periodic points. Right, so there's no degree consideration, it's just one 5-dimensional family of pairs. But of course, for degree, when we're doing in a space like this, which has dimension, whatever dimension it has, the space of all rational maps. I mean, of course, I'm working in a moduli space, but this has what? Dimension 2D plus 1, so that's 4D plus 2. But actually, really, I'm thinking of it mod Möbius transform simultaneously acting on these. So it's really, the moduli space should really be is a 4D minus 1 dimensional space. In any case, it depends on the degree. It's growing. It's more and more complicated. OK. So in this next slide is where hopefully it'll relate back to a lot of the other talks of this conference. And I apologize for the handwritten slide, but I just got tired making the computer graphics, and it was easier to write some of these things by hand. OK, so I said that our proof is using ingredients from the theory of stability in complex dynamics. It's not directly using those ingredients. It's working in a parallel world. So on the left side here, I have some pictures, some objects associated to what I'm going to call classical bifurcation theory, which is the theory that we know and that we actually work with. What does it mean for a holomorphic family of rational maps to bifurcate? And let me just say a little bit. Since we're in the Ricardo Magnier auditorium, I guess it's only appropriate to mention his role in this. His name appears first here on my list of, I just included some of the names of people that proved results that are directly related to the parts that we're using. So of course, as has already been mentioned in Miriam's talk, the work of Magnier, Saad, Sullivan, and Lyubich, laying the foundation of what it means for a family, a holomorphic family of maps. Let's say you have F parameterized by some lambda as a family of maps on P1. Here, they depend holomorphically on some parameter. I'm calling my parameter space S, just because that's what they do in the arithmetic side. My parameter space is S. This is, say, some complex manifold in general. But in the setting that I'm interested in, I'm actually going to always assume that it's a stronger object. It's actually algebraic. So really, it's a quasi-projective algebraic variety over C, okay, which in particular is a complex manifold. Smooth, irreducible, doesn't matter. I'm not going to write all the words down. In any case, we know what it means. That most everybody in this room knows what it means to be stable. The Julia sets in the family. So here's this picture of F acting. So F lambda is the family. I'm denoting now F to refer to, say, the map on this one dimension higher space, which is now holomorphic. So this is sending lambda z to lambda f lambda z. Okay, so I'm just packaging them all together into one space and one map. And that's what I call F here. And the stability means that the Julia sets, which I've drawn as a messy green thing, the Julia sets are moving holomorphically, as Miriam told us in her talk. Bifurcations correspond, so when that holomorphic motion fails to exist, corresponds to when the critical points pass through the Julia set. Okay? The bifurcations happen when critical points pass through the Julia set. And there's a way to quantify these bifurcations by thinking about, by taking the measures of maximal entropy on the fibers and seeing how the critical locus interacts with those measures and then projecting down to the parameter space. So this T sub bif here is one way to define what's called the bifurcation current on the parameter space. So this bifurcation current is a 1-1 object. It's not smooth, so remember, I'm not saying a 1-1 form. I'm saying a 1-1 current, but it's basically the same idea. And this T, the thing that I should probably define here is this, because this is important here, is this 1-1 current TF hat. So let me just tell you briefly what that is. How much time do I have? OK. So this TF hat is what's referred to as the dynamical green current on the total space. So this TF hat is a positive 1-1 current, closed positive 1-1 current on this complex manifold, which is the total space S cross the Riemann sphere, cross P1. And what is it? Well, we just simply, it's the 1-1 current where you piece together the measure of maximal entropy into a family. So every slice, so one thing that sort of describes it is that if you restrict to a slice, this is just what we often denote as mu f sub lambda, which is the measure, the unique measure of maximal entropy, which we know to exist thanks to the work of Lyubich, thanks to the work of Magnier and Frère and Lopez from the early 1980s. But as an actual definition, if you'd like, what you can do is you can take, let's see, well, I may as well write down a definition. So consider the projection down to the P1 factor. Take a smooth form, a smooth 1-1 form, say Fubini-Studi form on P1. This is just a projection here. Pull it back to this space. So now I have a smooth 1-1 form on the total space, and then start pulling it back by the dynamics. And the statement is that these things converge in the sense of distributions oops, to this TF hat. That's what this is. Okay. Anyways, it has this nice property that on slices, you recover this measure of maximal entropy. This object here is just a current that records the intersection. This wedge is really just reflecting intersection. So I'm taking a current of integration across C. I'm just intersecting it with these Julia sets, and measure theoretically you get an object, project it down to the parameter space. That's a bifurcation current. Its support is precisely the familiar bifurcation locus that many of us in this room have worked with. This is, again, a 1-1 object on the parameter space, an object of type 1-1. Now, if this parameter space is higher dimensional, then we're often interested in the corresponding bifurcation measure, which is going to detect some notion of higher bifurcations. Its support sees a more complicated type of bifurcation, and that would just be the top wedge power of this bifurcation current. Okay. By the way, so it was proved, so the bifurcation current was something I had introduced in my thesis, but shortly after, Bassanelli and Berthelot gave actually a much nicer introduction to the bifurcation current, and they also introduced the measure in that paper and proved that it's non-zero on the moduli space of all maps, that this measure is really something, it's non-trivial, and it turns out to be something of interest. And then just a little bit later, in some work of Xavier Bouffe and Adam Epstein, they gave another argument to show this measure is positive by showing certain Misiurevich maps are in the support of this measure.
Wait, so what were you saying a priori, even when you constructed the currents to show that they were interesting, it was a priori possible that this measure could?
A priori possible. I did not look at the measure myself at all, and I had no idea if it was.
And the general formalism of currents would allow for that.
Absolutely, and often happens in certain settings, yes. Right, so a priori it could have been that, yes, when you take the top wedge power. For example, if you do something silly like take an isotrivial trivial family where they're all conjugate, of course this will actually be 0. But yeah, it could have happened that, yes, that you get that the current is non-zero, but its wedge powers are 0. And that does happen in complex analysis, higher dimensional, a lot. Yeah. By the way, I should mention, since it's not smooth, of course, the fact that you can wedge this thing with itself is already requires some thought. It's because it's not only a positive 1-1 current. One of the things that I had proved was that it has continuous potentials. So that is important in this whole story. In any case, so there's this what I'm calling classical bifurcation theory, the usual bifurcation theory. And what we're actually working with is a parallel story. Because we're dealing with pairs of maps, we needed some notion of pairwise bifurcation theory, where I'm not interested in studying when the critical points pass through the Julia set. I'm interested in studying when a Julia set passes through a Julia set. So now I have two maps, or rather two families, two holomorphic families of maps, G F lambda and G lambda, where lambda depends on this parameter in an algebraic way, in this algebraic variety, and want to understand the intersection, the measure theoretic intersection. And it turns out, sort of to cut to the end of the story, that uniform bound we prove, the machinery, even in the abelian variety setting, all of those proofs rely really on showing that a certain measure, namely this one, is non-zero. So those uniform bounds, okay, via some big black box that I'm not going to talk about at all, but ultimately rely on the input of having a non-zero bifurcation measure. Not just a non-zero bifurcation current, but the parallel, this pairwise version of a non-zero bifurcation measure. So that's what Mirto Mavraki, I never mentioned my co-author's name, sorry. This is all joint work, I should say. It's all joint work with Mirto Mavraki. So one of the real thing that we actually proved, the only thing that was really new in this argument, all the other pieces we're really taking from elsewhere, is that this measure turns out to be non-zero on the space of all pairs, we get a non-zero measure. But this is the object we're actually working with. So again, we're intersecting Julia sets, measure theoretically, for two different families of maps projecting down. Maybe it's just worth mentioning one more thing. I see I have 5 more minutes. So I want to, before I go to the next slide, to give a little more context. I haven't even said anything about why I'm restricting to an algebraic variety here. That's related to the proofs. But one thing that you're familiar with, and so I just want to mention this, you know that on the classical side, so one of the main reasons I put McMullen's name on the left side was the following result. Is that we know that if this is, so now I'm going to use this hypothesis. If it's a family, an algebraic family, so F is a morphism, S is an algebraic variety, and this is a morphism, so in the algebraic setting, the theorem was that stability in the whole family can only hold for Lattès maps. Okay? Lattès maps, as you deform them, they don't bifurcate in a traditional sense. So, or an isotrivial family. So I'm going to write it not the way he proved it, because the bifurcation current didn't exist at the time. But let me just say, I'm going to write it this way. No bifurcations on this parameter space in this algebraic setting, if and only if F, the family, is either trivial. Actually, I'm going to specifically say isotrivial to mimic the language in the abelian variety setting. So isotrivial, which just means they're all conjugate. They're all conformally conjugate to each other. So either isotrivial or a Lattès family. This is building on Thurston's classification of the post-critically finite, the rigidity of post-critically finite maps. So these are the only options in this normal setting. And so I just want to mention one can prove an analogous result. One can prove an analogous result on this side. So it's just interesting to observe. I'm going to say theorem. I'm not going to attribute it to anybody, but there are actually many different results that go into this statement. But one can prove a similar theorem. Again, in this algebraic setting, so I have a family, holomorphic family, parameterized in this way. The coefficients of these f's are all meromorphic functions on some underlying algebraic curve or algebraic variety. What's the statement? The statement is that this current, this bifurcation current on the parameter space is 0 if and only if what? If and only if actually the maps are the same. Oh, sorry, I forgot to say. The pair is either isotrivial, conjugate both of them and they're constant family, or they are persistently related. This is the algebraic, I'm using this as proxy for there's a relation satisfied between F and G. They might be Lattès maps from the same family of elliptic curves, or they might actually share an iterate, or there might be some symmetry. But one can prove a similar result, but using somewhat different ingredients than what's used to prove McMullen's theorem. But that's just to give you a sense of what to expect here. Yeah? Sorry, what? Right, exactly. And that was the point of saying, there is some exceptional subvariety that we have to throw out along which this will be satisfied. So those will exist. I want to throw those away and then get this bound for all of the others. Yeah. So this is a sort of parallel result that one can prove. And so now, in the last few minutes, I just want to show you. So what I've been thinking about most recently, of course, while writing all this up. Again, as I said, the goal of the proof was of the main theorem was to prove that this measure is non-zero. We mimic the proof that Xavier and Adam gave about Misiurewicz maps. And in fact, we're also copying some ingredients that go into a proof that bifurcation currents are positive for higher dimensional dynamical systems. I'm presenting this as a theorem about one-dimensional dynamical systems, but actually, if you think of this pair, it's really acting on the surface P1 cross P1, so it really sits more in the world of higher dimensional dynamics. And so we're actually building on some work of people, you'll recognize these names, who have spent a lot of time thinking about dynamics in higher dimensions.
In some sense, I mean, I think later work of other people minimized it, but at least in what was written with Xavier, we were invoking aspects of friction and rigidity.
Right, and we do not.
Right.
We do not.
I think that was removed.
That's right.
Transversality was not, it was dimension 0 that was.
Exactly, but so the first proof that we have actually used that. And then we went back and realized, oh, we could also simplify our proof and eliminate the need to use transversality explicitly. But yes, and so, but I think it's important to mention, because the idea is here about how to, proving that this bifurcation measure is positive or proving that certain points are in this measure. And that's what we do here, is by proving that certain pairs have to be in the support of this measure because, just like similar to Misiurewicz maps, because they share a lot of common preperiodic points that are rigid. So the analog of the transversality statement is a rigidity statement about sharing common preperiodic points. So I won't get into that. That's a whole other story. The last minute, I'm now over time, I want to share an image because it's hard to have a feeling for what this object really is. So here we have lots of pictures of what the bifurcation locus is. For example, the boundary of the Mandelbrot set in the quadratic family. But it's not so easy to know what the analog, the bifurcation locus, even as a set, would be when you take pairs of maps. And so, earlier this week, Caroline Davis, where is she? Sitting in the room, here she is, produced an image, a really nice image of an example. This is the first example I'm seeing that's not a Lattès family. The Lattès pictures are just all black. That's not a Lattès family of a bifurcation locus. So just, I'm over time, but I just want to tell you what this example, I say what the example is. So in this example, my parameter space is the complex plane. I'm taking one of the families, F, to not depend on the parameter at all. It's just constant map z squared. So it is an isotrivial family, just z squared. The other family is the quadratic polynomials. And what is this? And there's some bifurcation current or measure living on this space. What's shown here is the support of this measure in black. In other words, it's not the boundary of the Mandelbrot set. It's the whole Mandelbrot set is in the support of this. There's a probability measure distributed on the Mandelbrot set and on these beautiful rings that go in and out of the Mandelbrot set. And this whole set is indicating the support, and in some sense even the distribution in some way, of what this measure is. And again, just to say, what is this measure detecting? It's intersections of the Julia sets. This is a plot of when do the Julia sets of the quadratic polynomials intersect the Julia sets, which is just the circle in this case. When do the quadratic polynomial Julia sets pass through the unit circle? And that's the plot that we're seeing. And that's exactly the support of this measure in this one example. So this is the first example that I have of something that's not a Lattès family. The Lattès families, with other things, bifurcate like crazy because their Julia sets are the whole sphere. So there's lots of bifurcations in Lattès families when you do pairs. But in this case, this is, anyways, the first example that I have, and I was actually really excited to finally see a picture of it. And I think there are a lot of interesting questions there about this pairwise bifurcation structure and what it means, and then the associated measure and the intersections of these periodic points. So sorry, there was a question, and I saw your hand up, and I kept talking. Yes?
I was wondering if you know anything about where those rings land on the...
I don't know anything yet. I don't know anything. So there's a lot of structure here, and what you're seeing is of course, the Julia sets on the outside of the Mandelbrot set, they're going through a holomorphic motion. And so what these rings are is when, for example, let's say you're following some periodic point in your Cantor set, and that's, of course, a complex picture, but then for one real analytic subvariety, that point is in the unit circle. So it's the intersection of the motion of a point in that Cantor-Julia set with the unit circle. Now, where and why they crash into the Mandelbrot set, I don't know. I just feel like there's a lot of questions. And we could have done this not for z squared, but for, say, the basilica, or in fact, the whole family in some way. There are all sorts of other variations that one can do, and you get different measures and different pictures. And I don't really know anything about them at this stage.